It happens all the time. It's that darn gravity. In archaeology, we study the past. A full vessel like this can tell us a lot. But what about something like this? Ceramics are some of the objects we find most often at excavation sites, but they're almost never intact. So what makes some survive better than others? Well, we know that how ceramics are made impacts how durable they are. One key part of producing ceramics is heat. I wonder how the firing temperature of a ceramic impacts its durability. You see, Messier Bernal and other archaeologists have found that we can actually figure out at what temperature ancient ceramics were fired. This is interesting because if we know at what temperature a ceramic was fired, and if we know how that temperature affects the durability of the ceramic, then we can better understand how that ceramic has withstood the test of time and how to take better care of it in the future. So let's break it down. Figure out how durable these ceramics are. So the way we're going to do it is we're going to see how well they hold up on the impact of a ball bearing. So this is our chute of doom. We're going to drop ball bearings just like these from this height down the chute and onto our ceramics below. And we're going to see the number of falls that it takes for the ceramic to break. The more falls, the more durable the ceramic is. It'll look a little bit like this.
We have to start by getting our materials. For our project, we reached out to Maish, a master potter and friend of the Yale Archaeology department. Alongside some helpful tips and tricks, Maish gave us 3 types of clay, including 2 types of stoneware and porcelain clay. All of these clays are natural, high-fire clays. Using natural clays allows us to most accurately replicate the clays that communities of anthropological study would have used, and having them all high-fire allows us to fire them at the same time. We elected to use the dark stoneware clay and porcelain clay for our test subjects. We chose to use 2 types of clay to eliminate the type of clay as a variable, which would allow us to better generalize our results to a greater variety of clays. We also needed ball bearings for the impact test, which we ended up getting from Amazon. We only needed about 3 for the test, but it turns out it's cheaper to buy about 500.
From here, we got to work making our pottery test samples. To make our test samples uniform, we used Dixon Ticonderoga pencils, the best pencils in the world, to roll out our clay to a width of 1.6002 centimeters. Then, we traced small discs using a cup that we stole from the lab. Once completed, we had about 15 discs of each type of clay, for a total of 30 discs.
Then we grouped our disc by the independent variable, also known as the firing temperature. In determining at what temperature to fire our clays, we were a little at the disposal of the most accessible kiln that we had. We used the Scott electric kiln in Pearson College to fire our discs, and because their kiln is used by other students as well, we simply had to fire the ceramics at the temperatures that the Pearson kiln offers. The first temperature was the temperature at which glazed pottery is fired, at 6 cone, or about 2230 degrees Fahrenheit. The second was the temperature at which bisque clays, or clays without glaze, are fired, at 0.06 cone, equal to about 1816 degrees Fahrenheit. We tried to fire a third group at another temperature, but we ran into some issues with that.
And then set to run. Press the page to show the actual temperature.
Okay.
Here goes nothing.
So instead, our third and final group was our control group, which was not fired at all. All of the ceramic discs were allowed to dry for a minimum of 5 days before being fired, and then were fired as is, with no glazes or inclusions added.
After reviewing our drop results, we found that there was a happy medium for firing temperature and durability. The unfired clays broke the quickest, taking on average 4.6 drops with a 3/8 inch ball bearing to break for both the stoneware and the porcelain. The fired ceramics needed a few more drops to break, and we needed to up the size of the ball bearing. Except for one outlier, 11 drops ended up being a reasonable threshold to set before moving up to the larger, 1/2 inch ball bearing. The high temp clays broke after taking on an average of 2 drops of the larger ball for the stoneware and 1.5 drops for the porcelain, following the first 11 drops with the smaller ball. The bisque temp clays were overall the most durable, needing 4.4 drops of the larger ball for the stoneware and 2.8 drops for the porcelain to finally break.
So, this tells us that firing temperature does play a role in durability, and that medium temperatures, such as the bisque temp, are best for making ceramics most durable. While any amount of firing will make a clay more durable, high temperatures, like glaze temps, should probably be used exclusively for clays with glazes or inclusions, such as shell pieces. This tells us that we need to be most careful when handling historical ceramics that are unfired or fired at high temperatures without glazes or inclusions. We can also infer that ceramics we find at research sites that are intact might have been fired at medium-like temperatures, or were able to endure even more post-depositional disturbance than unfired or extremely high-fired ceramics.
So, what did we learn?
Well, clearly based on our tests, firing the ceramics at all is making them more durable compared to unfired ones.
Yeah, we saw with our test that the unfired pieces broke far sooner in the experiment than those that had any firing, both the bisque and the high fire.
However, we propose that if other elements were to be added to the highest fire temperatures, like a glaze or inclusion, it might change the durability.
Bill Nye the Science Guy.
Science rules.
Bill Nye the Science Guy.
Inertia is a property of matter.